Okay, so as mentioned just before, we're going to be going into concrete structure and envelope, so in terms of concrete footings. So footing and raft slab construction. Yeah, some fantastic examples up there. I don't know if any of you spent any time in Europe. Had a look. Yeah, plenty of nods about the place. What's here on that though? Very extreme example, but you get to see that in some of the older, medieval cities around Europe. Just these, I guess, essentially fairly flexible forms of buildings that have sunk into the earth over the millennia. And also, for any of you who've been to Greece, or actually even throughout, just all throughout Europe, are the remnants of Roman civilizations. Just dotted about the place. I lived in a city called Nijmegen in the Netherlands. You can't dig a hole without hitting the Roman ruin there, basically. So even in the Netherlands. So, engineer's responsibility. So the engineer undertakes the following tasks: compilation of the footing report, footing inspections, inspection of trenches, and footing steel. So our trenches into the earth, they will basically comprise the formwork for any of the concrete which is subsurface. So the quality of our trenches, the shape of our trenches, will dictate in part the strength of those footings, and will also dictate in part how much concrete we need. So the engineer will specify minimum sizes of beams. And so let's say an engineer says 300 wide beam at 900 deep. The 300 wide part of that should be fairly easy for the excavator driver. All of the excavator buckets come in increments of 150 millimetres. So your really skinny ones, your 150 mil bucket, and you go to a 300 mil bucket, to a 450 bucket, to a 600 bucket, and a 900 bucket. You get some wider buckets as well from there on, but you don't use those for footings. So the sizes of footing beams as specified by the engineer correlate quite well with, obviously, with the size of your buckets, and that's no coincidence. But where it gets tricky, the excavator drivers, is in getting those trenches nice and neat. When we order concrete, we have to order a little bit extra to compensate for those rough edges, etc., because you end up digging out a little bit more soil than what you need. Hopefully you don't dig out less soil than what you need. Does that make sense to you all? So the engineer will want to inspect those trenches, because those trenches dictate what the footings are going to be, what the shape of footings are going to be. And they're also going to want to inspect the steelwork. So within our trenches, our stage of producing a footing, and I'll just get a marker out. Yeah. Now, fortunately, I had the materials and methods class in here earlier today for the diploma, which is a little bit different, but there's some crossover. So we've still got a section up here, a very rough section of a concrete raft slab. So within our concrete raft slab, if we're going to cut through it, so this is our ground here. Well, typically we'll scrape away the top layer of soil, all the dark soil that has all the organic matter in it, all the humus, because that's fairly compressible. Get rid of that, and we'll talk a little bit more about that later. I'll show you some horizons of soil. Get rid of that, so we've just got natural earth. Then we'll bring in some compactable rubble. So bits of aggregate in a good clay sand sort of mix that when it's wet and compacted, it sets nice and hard. So we've got our layer of compacted rubble in here. On top of that, we're going to put about 50 millimetres of crusher dust or dolomite, that really grey, fine dirt with lots of tiny little flecks in it. Has everybody seen that? You probably would have seen it on your way into TAFE. Tonight, they set sections of it down before they do their paving. So we nice 50mm covering of that. Then our excavator digs a trench through that, let's say it's 600 deep. So, and 50mm of crusher dust on top of that. Then, once our trenches are excavated, we put in vaporproof membrane, so that orange plastic, 0.2mm thick orange plastic that goes down, and then we put in our steel work. So these are our reinforcing bars, and that's what provides us with the tensile strength in our concrete footings. Concrete is fantastic in compression. You get a piece of concrete, well, sort of with your own strength, you're not going to be able to compress it. But even under huge forces, concrete resists compression really well. What it doesn't resist well is tension. So got a concrete block, try to tow a car with a concrete block, snap that. It doesn't take a huge amount of force to pull concrete apart. That's where the steel comes in. You get a steel bar. You can put a lot of newtons of force onto a steel bar without deforming it, and then you cast that steel bar, as a deformed steel bar, into the concrete. It bonds nicely. That tensile strength in that steel helps resist any flex of that slab. So we've got our vaporproof membrane, we set that in, and then we set in our bars. What holds our bars in place are these things called ligatures. So they're wire ligatures, cages, that hold all those bars in place. Now, that's for a pretty reactive sort of site. Let's say there's 16mm bars, we've got 3 of them on the bottom, a couple on the top, well, a couple toward the top, and then 2 right up top where our slab mesh comes across. That's a fairly extreme example. Your more common example is going to be something like, I'll leave that one in the corner, something like that, 12 bars. So that's what goes inside our slab. And an engineer is going to want to come out to site to see that actually goes in there. Because once the concrete is cast, it's pretty final. Once the concrete's poured, there's nothing much you can do about it. Turns out a cousin of mine who's an engineer down in Tassie was just a few days ago relaying the story of there was a Bunnings warehouse they did down there, and they did that incorrectly and had to jackhammer up the whole thing. That's very, very expensive. You don't want to be the contractor responsible for that. You probably don't want to be the engineer who let that go through either. So the engineer's going to want to see that those bars are in place, because once it's all set in concrete, it's set in concrete. They will also do floor slab design. Now, not all structural engineers will take on floor slab design. You need specific insurance for doing that. So you will go to a structural engineer that has the insurance for doing floor slab design. They may do roof truss design calculations. That does happen, but typically that aspect is being palmed off now to truss manufacturers. You've got truss manufacturers like Mytech. They've got everything in-house. Within the engineering office, you might go, okay, this is an indicative truss layout. You send that off to a company like Mytech, and they do all the calculations and all the specifications, and they'll produce a truss layout diagram specifically to what they've designed. They will do retaining wall design. So any retaining walls that are in excess of 1 metre in height have to be engineered. And typically an engineer will establish the worst case situation and designs the building elements to resist that loading. So engineers by nature are going to be conservative, but that's what they have to do to maintain their business. So the forces we can look at in 2 main categories, or the loads typically, dead loads and live loads, when we're talking about gravity placed on a building. So dead loads are things like the wall, floor, roof elements, part of the building, air conditioning, hot water units, anything that is predictable and built in. So anything we go, or anything that we can design for, we say, okay, these are the building elements we know are going to exist when we're specifying the building. These are all of our dead loads. They're the predictable ones. The others are live loads, and they're loads due to occupancy of the building. So people, furniture, vehicles. Can anybody else think of any other live loads? There may be. You on that? Actually, what is a bathtub? Is that a live load or a dead load? It is definitely a grey area. I put a bathtub under dead load because when you specify a bath, you know the volume. You know, okay, 200 litre bath, it's going to have, 1 litre, 1 kilo. 200 kilograms of additional point load when it's full. So I would chuck it under dead loads, but it's one of those things, right? It's about, occupant's behaviour. But other live loads, so what about a piano? Yeah, a live load. Yeah, because that's, it's whether the people want to bring a piano in or not. So there are some of those things like piano, particularly heavy objects, we can't really design for. Yes, your building has to be able to have, the addition of a piano or I don't know, whether really heavy objects, gym equipment, something like that. These are fairly predictable, not out of the realms of possibility. Things that occupants are bringing to the building.
Is there a standard that you need to predict for, like a certain
live
loads?
So that is incorporated within either the timber framing code or within the steel manufacturer's specifications. So timber framing code we have learned a lot about, and that specifies members, all these floor members, to be able to take certain predictable loads. So there's some, I guess, when buildings are occupied and used in a fashion that you can't predict, well, the timber framing code is not going to bring that into consideration. They're not going to think, oh, okay, somebody brings in a really big diesel generator and parks that in a residence. That typically doesn't happen. We can't, the timber framing code can't take that into account. But any normal occupant behaviour, yes, the timber framing code, takes into account. But if you know that people are going to be adding some things, if you know that there's got to be a bathtub, putting it up in a top story bathroom, add additional floor joists there. It's cheap to do during the construction. If you know that there's going to be a gym on a suspended timber floor, put in some extra floor joists. Bring your joists closer together. Be conservative about that. But typically, the predictable for your predictable live loads, it's taken up in the timber framing code, or within the.
There's a higher rating for ceiling storage.
Yeah.
I think if a floor's about 1.5 tonne for a certain area. So if you want to do storage in your ceiling, it's 2.5 tonne.
Yeah. Yeah.
I don't know how you achieve that.
There's a lot of books.
Piano in your roof, but
Yeah. Well, books actually. Books. Ever lifted a box of books? I encountered a fairly interesting website just recently. I'll try to. How do I go about adding it? Here we go. So, and I'm sorry I didn't think of that now to go incorporating it. I'll have a quick search to see if I can find it. Calculator. Stanman. So, look, not independently verified, but an Australian website, somebody has gone on and produced weights of individual building elements as per Australian standards. So he's gone in, taken them all from there, and then tabulated those. Now, okay, it's an internet resource. I can't verify that, but yeah, might be quite a good resource or something for you to check out. So yeah, it's an interesting thing I found on the net that relates to all of that. So we've got our dead loads and live loads. Also acting upon a building are wind loads. So you've got wind pouring over a building, and is that a clear enough diagram for people to see? You can see that fairly clearly. I guess you've got it in front of you there as well. So on our building, we'll have a windward side and a leeward side. You know, that's going to change throughout the days and the seasons, etc. It depends on the wind direction. But just simply in talking about how a building reacts under wind, we get both uplift as the air gets pushed up over that first piece of roof on the windward side and then passes the ridge. On the leeward side, it starts sucking and starts pulling at that roof. So you actually get uplift. It's operating in not the same as an airplane wing, but there are some similar elements to that. So it starts pulling on that roof, trying to lift the roof. So we have to design for uplift. The way that we design for uplift is, if we were to do a timber frame, through the timber framing code, it specifies tie downs for certain forms of construction, for certain roof load widths, within certain wind speed categories. It gives you the kilonewtons of restraint that you have to counter with your tie downs, and then it specifies the tie downs that will meet those kilonewtons of restraint. So, working through the timber framing code, we can design for this uplift that happens, and it actually, I guess, how many? I think I've seen about 6 or 7 roof failures in about as many years doing repair and reinstatement work of roofs actually being removed from buildings, ripped off. So it certainly happens with the inadequate tie downs. I've never yet seen it for a tile roof though. All those have been sheet roofs. Still, you have minimum tie down requirements for tile roofs as well, not nearly as extensive as they are for sheet roofs though. So we've got that uplift force happening, and that uplift force not only happens in the roof, well, we've got that uplift force happening on the roof, but the roof has to be tied down to the wall frames. The wall frames have to be tied down to our floor frames or footings. So those tie down, the continuity of tie down has to happen all the way through the frame. But not only do we have uplift happening from wind, we've also got a racking force. And a racking force is essentially what's pushing on the side of the building, what's pushing on the side of the building, and also pulling to an extent on the side of the building. It's making that lovely square building want to do that. So as we blow wind, and so we need to counter that with bracing. The thing is, typically there are 2 main types of bracing employed in a house frame. One of them is strap bracing, and within your timber framing code, you'll see the type A, type B, type C, type D, type E, type F. So there are all these types of bracing. The one that's typically employed is type D bracing. It's where you've got a very dry marker. It's where you've got 2 metal straps. And has everybody seen metal strap bracing before? Any no's? I'll take that as everybody's seen metal strap bracing. Type D bracing has our metal strap, which is 0.8 by 30mm galvanised iron strap. And we've got our studs go vertically here like that. And off the top of my head, maximum run for the bracing is 2.1 metres. So we've got strap going that way, strap going that way. Our bottom plate's of course fixed to our slab very strongly. Our bracing is looped over the top plate, nailed with, like, let's say four nails at each, or 2.8 diameter nails. But the important thing is we've got bracing happening in this X fashion. When we get this happening to our wall frame, so a deflection from square, so our bracing is going across like that, this steel strap has to be stretched significantly to allow that to happen. And that's the way it works. So if we were to run our bracing straight up and down or directly horizontally, it would do absolutely nothing when we're trying to elongate that square. Does that make sense to everyone, and how that bracing works? And you'll see that same principle applied in so many scenarios. Like anybody driving. Well, next time you're driving past like a rural fence, like fencing in a rural area, you've got your cyclone mesh down the bottom. Well, the way that your strainer assemblies are constructed now with fencing is you've got fencing going this way and it's strained up that way, so it's pulling in this direction like that. So you have a post here, you put in a solid post at the top there, and then you have a wire going in that direction like that. So as that fencing pulls this strainer assembly, you've got that wire that resists the elongation of that square. You see that same thing happening everywhere, that diagonal bracing. So that's what's called type D bracing. The other type of bracing that's commonly employed is, I think it's type G bracing, which is your sheet bracing. So we've got plywood sheet, and that plywood sheet is nailed on to our studs in this fashion. Has anybody seen that before? On a timber frame of a house, you've got sections of plywood nailed on to that timber frame. So this bracing provides, I think it's about 3 kilonewtons per linear metre, so 1 metre to 2 metre, 1 metre to 2 metre, 0.1. That's 6 kilonewtons per linear metre. So sheet bracing provides a lot more lateral restraint than our simple type D bracing. Has its limitations though. It's a little bit more time consuming to install. Like you can buy a roll of sheet bracing, 30-metre roll of sheet bracing for like $10 or whatever. That you can do your whole house. Yeah. I was, yes. Okay. Yeah. Oh, great. So, do I have to go downstairs to get them to turn the PC on, or?
No, you could just open the door and just turn the PC on. The doors are unlocked.
Okay. Oh, underneath the
Yeah,
desk.
just underneath the desk there.
Oh.
Yep, so just open the door and the PC part on duty to be put in.
Okay. Cheers. Well, thanks for finding me and sorting that out. Thank you. Right. So your type D bracing is going much cheaper, much simpler to produce. Also, your sheet bracing, that's fantastic for brick veneer dwellings because you've got that gap and then your bricks on the outside. If we're doing a sheet wall cladding on top of that bracing, obviously, we either brace a whole wall or we do bracing and then we pack out all the other studs. By that 10mm all the way along the wall has its limitations. So that's our wind loads. Our other loads, thermal loads. Well, it's not thermal loads, so it's not essentially a load in much of a physical sense, although it can have a physical impact. So typically with steel sections of building, so steel framing, meets steel sheet roofing, you get expansion and contraction under heat. And with, if you live in a house with really long steel sheets on your roof, or even some of these really big hay sheds, things like that, you can hear them making creaking noises as a cloud comes over in front of the sun. That's how much they move under the heat. Also, earthquake loads, not a significant one in South Australia. We, from time to time, will have an earthquake happen, but it's really pretty much a non-event here in SA, as with snow loads. So we've had snow maybe a couple of times while I've been living in Adelaide. It's not a major event here. So loads are measured in newtons, but in a building they're measured in kilonewtons typically, because we're dealing with fairly large weights and large forces. So force is a push-pull action that tends to produce motion, tension, or compression. Forces in buildings are referred to as compressive force. So that's an act on a body, tends to shorten a body or push parts together. For example, a column under load. A tensile force is a force that acts on a body such that it tends to lengthen it or tries to pull the body apart. So it's a tensile force. A shear force is two opposing forces trying to slide one body over the other. So, in terms of scissors, anybody heard of scissors being called shears before? So you've got a pair of hand shears. What they're doing is it's two bodies acting right next to each other, causing a shear force. And and when you're typically in Adelaide, we've got fairly reactive soils, and when we're building masonry, it becomes quite obvious at times. Probably many of you will have seen, so with older brick buildings, you get cracking in this fashion like this, in that stepped way up a building. And that's normally indicative of, some swelling and a bit of uplift in this area here, or far less common is some shrinkage in this area here, causing a building to do that. You can also get diagonal cracking in that fashion from uplift in this area as well, pushing things apart, but typically it's in reverse. However, what you will get sometime, and what's the more important thing to look out for, where you've got brickwork like this, and you get shearing through bricks in such a fashion, or it's a little bit jagged or whatever. But when you get that cracking that's happening vertically, that's telling you that there's a real concentration of forces happening. So we've got either a lot of uplift here or a lot of subsidence here. Something has gone significantly wrong when you get cracking straight up now, and that's what's known as shearing. So where you've got two opposing forces force the body to part and slide over the other part. Also, deflection. So that's displacement away from a straight line. So beams under load displace vertically. So we've got a big beam coming along here like this. We put a load on that. It's going to want to do that. Typically, deflection is measured in millimetres. The reason it's measured in millimetres is that building elements, the minimum sizing for building elements is typically designed to avoid deflection. When it comes to steel beams and the like, we can actually put a whole lot more load upon that steel beam than what the manufacturer's literature designs it as, without it failing. So you can get a huge amount, but what you get is deflection. And you cast your eye around TAFE here, you won't see, well, I certainly hope you won't see any visible deflection of members at all. We could probably put far greater loads on this building and on elements of this building, but then we would start to see sections sag and move, and that's undesirable in building. Undesirable, but not necessarily dangerous. So, some definitions. So, a foundation, that is the rock or soil found in its natural state on a building site. So, a foundation, that's what we build upon. The footing is what we use to build upon that foundation. So, let's say a good definition of that is the lowest element in the structure in contact with the ground. Distributes the total load of the building. So the footings distribute load to the foundation, which is the soil. That foundation can obviously be modified. We can cart away a whole heap of that soil and we can bring in soil. We can bring in some compactable rubble, compact that in 150 mil layers, and we have a much more solid foundation for, placing our footings. Some different types of footings. So we've got integrated, which is where we've got, as the name suggests, integrated members. So raft slab, which has beams with a slab integrated, or piers integrated to a slab, or pier and beam, where we've got piers integrated with a beam. We've got continuous footings, so that's like strip footings and beam footings, and isolated footings, such as pads and piers. And we'll get into those separate types of footings a little bit later on. So soil profiles. Stable soil exhibits little movement and provides a stable base. So not a lot of that in the Adelaide metropolitan area. There is a bit of that. In fact, what I'll quickly do is have a look and see. I'm pretty sure we'll be able to find a soil map for Adelaide. I'll just do a quick search of that. So we've got in images. Clear one. It's going to take a little while to come up. So we do have some sections of stable soil in Adelaide. One of those sections, well, actually we can sort of see it on here while we're waiting for the internet to open up. Well, that's much better. So we've got fairly stable soil that follows in this fashion. Does anybody know what's running down there? The torrents. Yeah. So as the torrents, over time, it's brought in soil from up in the hills, from 6th Creek and 5th Creek as they feed in there up Gorge Road and whatnot. They're bringing all this soil down from the hills where we've got more weathered rock, less clay, etc. It's bringing all that down and it's depositing it. It has a flood time and time again, deposits all that soil along there, and then you can see it sort of bells out there. I don't know, where's that Henley Beach area? So it's deposited. So that's fantastic soil. Well, it's fantastic for growing on as well, growing food, but it's also fantastic soil for building upon. I had an engineer ask me. I was living in College Park, just there, and he goes, "What number are you on the street?" I told him. He goes, "Oh, you're in the good bit." So within here through to here, where you live on the street, you're in the good bit or the bad bit. So we've got some little strips of good soil throughout Adelaide. It's all a bit too small to see, but we've got some real shockers as well. So these dark areas, that's highly reactive soil. So that encompasses places like Ross Trevor and Newton. It's got what's in that northeastern bit there, Hillcrest. Can't think of any other ones there. But this area where you had a lot of timber frame buildings, brought over from Germany, put on stumps all through here, and they're doing a whole lot of that. But yeah, through here, under some of your cavity brick buildings, you've got some intense footings going on there. But then also so that's extremely reactive, those sections there. we've also got highly reactive through here. Has anybody spent any length of time in, or know people who live in Parkside or Unley, or any of these sort of inner eastern bits? Some lovely old houses there, but the thing is, we've got fairly reactive soil meets stone buildings with strip footings underneath. They're doing this sort of thing all the time. And although you probably pay through the nose for a house there, you also pay through the nose with upkeep and maintenance, because they're doing this a lot as well. So we've got a lot of areas throughout Adelaide with a fair bit of movement. You've also got issues down in the port as well for various areas there, because you've got some collapsible soils there, and also there's some issues in around here where they were mining clay, etc., and then chucking car bodies and all that sort of stuff back in the holes and putting stuff over top and then selling the land for building houses. But that's not necessarily due to the soil. But we have a lot of reactive soil in Adelaide. So reactive reacts with moisture, swells as moisture content increases and shrinks as it dries out. Soft, highly compressible, unable to support loads. We don't have a lot of that in Adelaide. Although bits of that down towards the port. And collapsing soils, so decreasing volume as moisture content is increased, can suddenly collapse. I had only experienced that once. We've got bits of that about the place. That's where people are typically building on deposited sands. Had a building out at Renmark, so out on the Murray River there, you get a lot of wind-blown sand about the place. They had a broken down pipe, sent water out next to the building. That water lubricates the sand particles, lets them fit together closer and better, which means the soil collapses and the building starts getting pulled, gravity pulls the building down with that. So you do get some examples of that happening about the place, but it's not common in South Australia. So council require a report before approval is issued. There are two types of reports. Your preliminary report, so identify footing type suitable for construction, used as pre-sale information, not used in construction. So that's just getting some soil samples to see, okay, this is what we're dealing with, but not necessarily suitable for an engineer to go through and inspect and produce a bore log. Your construction report, you get the soil samples done, and you take those soil samples to about 4 metres. I think the code asks for 3.5, but typically your structural engineers would like to have your soil samples taken out to 4 metres. So get your soil samples done. The engineer will produce a bore log, which is an assessment of that soil and its reactivity. From that information, they will detail the footing. Well, you have to provide them with the plans of the house so they know what loads are happening on there. They'll produce, they'll detail the footing type and site works. Other information they may need in this construction report are a contour plan, cut and fill information, and paving advice as well. The reason we want paving advice there is the engineer wants to know essentially what moisture the surrounding soil around that building is going to be subject to. So if we're going to have concrete paving to 2 metres outside the building, well then that vastly reduces the amount of moisture that's going to be getting into the soil there, and it reduces the extent to which the engineer is going to have to design the footings. The engineer will put it in their report that their specified footings with 2 metre wide concrete paving, and if that doesn't get produced, well then you don't have your insurance, or the engineer won't certify the work. Anything else? I can think of another thing that engineers might want to know about a site for footings there as well. It's a bit of an odd one. some of you might get it when it comes to moisture being taken out of the soil.
Trees.
Trees, yeah. Eucalypts are fantastic water pumps. They're great at getting water out of the soil. That's why they thrive in such a dry climate like Australia is, because they're really good at getting moisture out of the soil. Engineers from time to time will want to know the species of tree, how high it is, how wide it is, and how far away it is from where you're building the house. So that the drip line, the size of a tree's canopy, where the water comes out, is indicative of where the extent of the roots are as well. And the species of tree is indicative of how much water that species is likely to suck out of the soil, which means how much that soil is going to react throughout the year, when just from our natural rain and the removal of that moisture from the tree, typically in summer. So soil samples. Has anybody ever seen a vehicle getting around doing soil samples? Yeah. Seen? Yeah. So yeah, plenty of nods. So I think I don't know what's in the background there. That looks like a rather large machine, and they're rather large soil samples as well coming out of that. I don't know the millimetres, but typically soil samples we've got around that sort of diameter for your push rod. So methods of sampling: hollow spiral drill, push tube, and impact tube. So push tube's by far the most common, just located on the back of a Land Cruiser ute with a hole set up, put on the back there with a hydraulic push tube. Although there's, we had a scenario once where we had to take soil samples within the hallway of a house. So you take up some floorboards in the house, and the way that's done, so you take up enough, like the full width of the hallway of floorboards, and you use an impact tube, which is a tube that you put a little two-stroke motor with a hammer type scenario in it, and you whack that tube down, join another one on top, whack that one down, join another one on top, keep whacking that down, and then you set up a tripod in there, and you jack the tubes out, undo them, and tap the soil out like that. So these impact tubes, they can be highly mobile like that and get into fairly inaccessible areas. But by and large, your most common is that push tube, located on the back of a small vehicle. So site classification wise is a factor stated in the footing report which represents expected soil movement. Now, as we said earlier in the slides, engineers design to the worst case scenarios. Y values also, or should be, determined to the worst case scenario. So it's possible soil expansion given the presence of moisture. So Y value can be defined as the movement at ground surface level during the life expectancy of the building. And that will then help you determine your various classifications. So your common classifications are stable, moderately reactive, highly reactive, and extremely reactive. I can't think of all the Y values off the top of my head for that, but I think it's when you get a Y value over 100 millimeters, then you're into the extremely reactive. But then there's another category which is not too common, but that you place underneath that, which is called P class soil. So that's problem class soil, and you get a few examples of that. But that's where you go beyond extremely reactive. So that is typical bore log. I guess relatively typical bore log. What information do we get from that? This should be read in conjunction with a site plan as well. I'll just quickly so this is our site plan here. Our site, and some trees, whatever. We'll do a little thing like that, is that, it's probably a bit too small for you guys to see from back there, isn't it? Like an enlarged version of that is like this. Blacked out, and then we'll have next to that BH1. Another one of those jiggies, BH2, etc., etc. So this one's got 3 boreholes done. So we'll have 3 spots around the place, and that's because the reason, and then our other one here like this, because this is where we want to build the house. So we decide where we want to build the house, then we get soil samples done. We accurately measure and document where those soil samples have been taken on site, and then put that information onto a site plan to be read in conjunction with the bore log. So somebody goes, oh, hole 1, oh yes, that's that one there. Hole 2, that's that one there. Because when we look through here and look at the soil horizons, from those couple of boreholes, we can get a much better picture of what's actually happening throughout the site as well. Because we'll go, okay, there's this horizon of clay in borehole 1, which is about 200 millimetres deep there. By the time we get to borehole 3, it's like 300 millimetres deep. And then, if we happen to do another one down there, for example, we're at 400 millimetres deep, we know that there's this relatively consistent thickening of a horizon through there, and we can see that for all the various different horizons. So I've just mentioned horizons. That's what is listed down here, and this is the sort of thing that can really differ between engineer to engineer. This one has chosen to say horizon A, horizon B, horizon B1, horizon B2, horizon B3, horizon B4. The reason they'll split B into these sort of things is because they'll see, okay, there's a commonality with the type of soil between those horizons, but they're still distinct horizons. So they'll say horizon A, that's very different, we'll give that a different letter, whereas all these other horizons, they're really very similar. So instead of giving it a different letter, we'll just attach a number as well. Other engineers will just go A, B, C, D, E, F, G, etc. Depends. And then, so that's our various different horizons, that's our boreholes, and then right down the bottom, we've got our Y values. There's not a huge degree of variation on this one, so our smallest Y value is 54, our largest is 65. But there are 2 things to take into consideration with those Y values as we get them. So we'll design, well, the engineer will design footings to this Y value, to the 65, or possibly to 70, which will be, I think that might just slip into highly reactive. So they'll design for that worst case scenario. But another thing that they have to look out for is we even get a worse situation if that one's, the Y value there is 65, but if this one is only 23 or something. Can anybody think why that makes the situation worse?
So you get reactive soil and a stable soil.
Yeah, exactly. You've got that heightened chance of differential movement. If all of your soil is reactive and you get relatively consistent exposure to moisture, it does this. But if one section's a big lump of granite and then you're onto clay for the next bit, you get that happening. And it's about the most dangerous buildings is where you get the differences in movement over a very short space in time. One of the things I used to do with the engineering office is go out and do levels around the outside of the building. So I pick a brick course, typically right down the bottom, with the laser level, go take measurements all the way around the building and then plot that up in 3D to see what the building is doing. So we've got some soil lifting and some soil movement, etc. like this. Now the largest variation I saw from one end of a house to the other end of the house in that time, actually the largest one I saw was about 200 millimetres, but but that was a very large, but a fairly small house. I saw 150 millimetres difference from one end to the other. So that's 2 bricks. So a brick plus mortar is 86 millimetres. So almost 2 bricks worth. So one end of the house is 2 bricks higher than the other end of the house from soil movement. But there was almost no discernible cracking in that building. There was some, right? So things had started to happen, and the people said, look, there's an issue that needs to be investigated. And the reason for that is that 150 millimetres, that increase was consistent all the way through the building. Yet you can have scenarios whereby there's only like 20 or 30 millimetres difference from one end of the house to the other area. But if that happens right at one point, you get some massive cracking through the building. So it's not always about the reactivity, it's about that difference in movement and how close those differences are together. So we're interested in these values down here, but also what we're interested in are the depths of these horizons, and that's what's shown in those numbers there. So in borehole 1, we've got horizon A, 400 millimetres deep, borehole 2, 350 millimetres deep, and bore 3, 350 millimetres deep. So pretty consistent throughout there. But then borehole 1 doesn't have anything of horizon B, doesn't have any of horizon B1, so it's straight to B2. So the horizon B2 starts at 400 millimetres deep and ends at 700 millimetres, so that's 300 mil deep there. Hole 2 and hole 3 do have the presence of those 2 horizons, etc. So that information enables us to essentially visualize a scenario like that for our soil. So borehole 1 straight through here, it's got horizon A, then it's got horizon B3 and horizon B4. Borehole 2 gets a little bit of horizon B1, etc. So we start getting an idea about what's happening in the soil there. Is that all quite clear? So all those numbers tell us what's down in our soil samples, and then from there on we've got soil description. So horizon A, silty clay, silt, dark grey, low plasticity. So it's fairly crumbly. It's not really sticking together. It's not very moldable. Silty clay, dark grey, high plasticity. Just hearing that, I think, okay, that's going to be relatively reactive sort of stuff. High plasticity, silty grey. And throughout that short amount of horizon, we've got, this goes a bit beyond my knowledge, but you've got figures here telling you how reactive those sections of soil are per dimension. But those sort of things are relatively high, and so they're going to contribute significantly to those Y values. Then silty, gravelly clay, brown, mottled yellow, medium to high plasticity. Gravel is variably weathered siltstone, so they're getting a little bit less reactive. So it gives a description of that soil, and then it's up to the engineer to determine from what they know about soil how reactive that soil is going to be in the presence of moisture. So they make that judgment. So concrete raft slab construction. Surrounding soil material must be kept stable to minimise movement. So that's what I was talking about with providing that perimeter concrete paving. Types of slabs, so slab on ground, which is by and large the most common, a pier and slab. So that's, well this, that there is a car park, an Undercroft car park. That's an elevated, suspended concrete slab floor, but it's not too dissimilar to what a pier and slab would look like if you took all the soil out from underneath it. So we've got our piers go down into the ground, and our slab sits on top of those piers. Sometimes that slab can be elevated from the ground and our piers go down, I guess essentially in that situation there. Or sometimes that slab will still be on the ground and then have piers going all the way down. We typically do that when we've got stable soil which is a long way down and collapsible soil up above. So there's no real support happening for that slab. You don't tend to do that when you've got stable soil and then reactive soil above. The reason you don't do that is because you might lock into that stable soil down beneath, but you've still got reactive soil wanting to expand and contract under your slab and causing issues with your piers. But certainly, there's a lot of that happens in places like the Netherlands, where they've built big walls and pumped all the seawater out and reclaimed land from the sea. But in that land that they've reclaimed, it's still, many metres deep. It's just this whole black, mucky stuff. If you put a house onto, I don't know if anybody's been to Amsterdam, you see all these old buildings sort of leaning against each other. That's why, because it's all built on this relatively soft, silty soil. And even to build those original buildings, those really old buildings, they got big pieces of timber and rammed them into the ground to hit some of the more stable, consolidated sand underneath, and then build on those. But the way you get modern construction happening there is with a big pile driver and steel piles, and they get rammed down into the ground, and then you build a building on top of it. Essentially not too dissimilar to that. So that's your pier and slab. Pier and beam, that's a bridge, but that's also a reasonably good illustration of what's happening in a pier and beam scenario. So we've got our piers happening like that, but then a beam across the top of those piers, and then our floor happens on top of that. You can have that happening, you can do that with concrete, you can also do that with timber. And it's quite common to see that scenario being done with timber, but can also be done with concrete. Waffle pod construction, does anybody know what a waffle pod is? Seen those? So a waffle pod was a system which was designed actually in South Australia. And in my Thursday morning class, I've got a guy from Gino's Engineering who comes in, he's a student in class there. And he said, we're doing waffle pods all the time in Victoria and New South Wales. How do you do them in South Australia? They're a South Australian invention. And it's a fantastic way of forming a concrete slab, except it can't really deal with a lot of the reactive soil that we have here. The soil we've got is just that bit too reactive for waffle pods. But that, if you dug away all the soil under a waffle pod, ignore the piers, that's what it looks like. And the way we create that is we get a whole bunch of these square styrofoam blocks, about this tall, like 300mm tall. I think 1200 by 1200 or 1190, so almost 1200. And then set them out on the ground like that with these plastic spaces that go between them. And then those plastic spaces, we run bars across the top of those plastic spaces, and then put formwork on the outside and pour concrete in there. And so you end up with a concrete structure like that, something that looks like a waffle. So that's a very good distribution of beams and connection to a slab, but it has its limitations. So with a lot of our fairly reactive soils, we'll do beams down to 900mm deep or so. So really deep beams to have one face a long way from the other face, gives us a lot more strength in a lateral fashion. You've got limitations with the depth of your beams with a waffle pod slab. But so that's what a waffle pod looks like. We might have some pictures of those styrofoam void formers later. But can everybody get that mental picture of what a waffle pod slab looks like when you're setting it out?
Is that a cost saving?
It is. So you pay a lot for the styrofoam waffle pods because somebody owns the rights to them, etc. They make their money. But you save a lot on concrete, so it uses a much less concrete. and then you also use much less steel as well, because it's a very efficient use of concrete and steel, because everything's equally distributed and regularly distributed. So with your standard, your concrete slab like that, you'll have a beam, and then your next beam is going to be 3 metres away, like that sort of distance. Those ones, they're 1200 millimetres apart. So a lot more of them, but then you need. It turns out you need a whole lot less concrete. And if you're paying $300 for a cubic metre of concrete, that adds up very quickly when if you're going to go through 120 cubic metres of concrete to build a slab. You're saving 20% of that. That's quite a sizable saving. And then once again on steel as well. So steel is very expensive. So our most common thing, if you were to drive around a new suburb, you'll see a lot of these. So slab on ground, raft slab with integrated beams, otherwise known as a stiffened raft. And this part of the lecture does get a little bit tedious. Well, so for this first bit, it's not so tedious. It gets a little bit tedious further on because there are many actual similarities between the construction of slabs. So I'll start off a bit slow, but then the other bits I might just rush us through a little bit more. So our stiffened raft slab. First of all, what we do is we clear the site, remove 150 millimetres of topsoil. So 150 millimetres, that's indicative. With our boreholes from that bore log we saw, our top horizon of soil was 400 millimetres, and we might have a lot of humus in that whole 400 millimetres. So it might be that 400 mil which comes off. So we cut it down to that. Then, topsoil contains compressible organic matter. Remove to an area of 1 metre around the building perimeter. So it's not just exactly where we're building the building, we'll do it further out. A few reasons for that is we want to make sure we get lots of stable soil around the building as well, but you also want a really flat surface for the people setting out the formwork to work on. If you don't have that lovely flat surface, it makes it far more difficult. So then you fill that site. So the soil you take away, well actually, it's probably best practice not to take that soil away, because that's a lovely soil for growing stuff in. If you want to have a decent garden later on that property, get that soil, put it in a pile out the back or out front, wherever you want, but set it aside for use in the garden beds. Then you bring in rubble to compact, so level and compact to bench level. So usually quarry rubble to do that. Compaction by wetting and rolling in 150 millimetre layers. That compactable rubble, it has to be wet to compact properly. Has anybody dealt with rubble before or seen that? Yeah, a few nods around. When you got dry rubble, try to compact it. It just sort of moves apart. It all moves around. But you add water to that, it becomes really quite stable, and then it compacts down to being really hard. If you compact your rubble correctly, it is really hard to break through with a pick. So you get your pick and you try to smack through it. You get a very solid scenario. So you bring and you compact it in 150 millimetres layers. So if we took away 400 millimetres of soil, but our bench level was that natural ground level, we would end up putting, probably 150 millimetres there, and then we'll bring in the whacker plate or the roller, and we'll pack that down to about 120 millimetres deep. Then do another 150, pack that down to 120 millimetres, etc., until we're up to that bench level. Then quarry sand can be used on the top 20 millimetres. So it says top 20. You've got depths of up to 50 millimetres with your quarry sand as that top section under your slab, because that's relatively stable stuff. It doesn't compact and set nearly as hard as your rubble. So your rubble gets sort of almost like concrete. It's not bound together as well as concrete, but it gets really hard. Your quarry sand or your dolomite, if it gets a bit wet, you wet it and you put it down in place, it holds its form really nicely, and you can get really nicely formed trenches. When you dig with the excavator, you get these lovely crisp edges to your trenches. So it saves you on concrete. So there we go. Actually, that's a really good example of that dolomite. Now I'm not sure what's under that. It doesn't look like they brought in fill there. That looks like natural soil. So we've probably got pretty decent soil there. We didn't need to fill it at all. But then they brought in dolomite, and you can see, you can get a lovely smooth finish and lovely neat trenches with it. So the edge of your trenches are quite neat. You can see this one down here, where we're just dealing with natural soil. See how the edges of those trenches are not very neat. So in that sort of scenario, you're going to have to add another 10-15% to your concrete order to make sure that all those little holes and gaps and all that sort of stuff gets filled in by concrete. What you do not want to be, or the scenario you don't want to run into, is being 5% short on your concrete order and having your slab 95% complete and then running short. I was on a site where that happened as well. We were building a tank next to a massive big machinery shed. They were concreting that floor, and then guys came over and asked us, look, do you have any quickset in your ute for doing this small patch? We're like, no, we don't. So they had to quickly get a mini mix in to do that last little bit. With that large floor, you can do that because you're pouring consistently throughout the day. But you do not want to be in that scenario with a residential site. Whereas that one, you're probably not going to have to allow too much more extra concrete for that pour because you've got much needed trenches. So you save money in that scenario. Set out an excavation. So set out using string lines at the edge, excavate the trenches, excavate set down areas. So where you've got your wet area set downs, you may need to have that set down in the soil as well, thicken your slab through that section there, and then organise engineer inspection. So engineers got to want to look at those trenches and look at the steel work to make sure it's all as per they're specified. Then excavate for service pipe trenches. Pipes passing through the footing beams are lagged. So you notice these pipes going through, where they're all horizontal through a beam, they're lagged. Where it's going vertical, it's not lagged. Can anybody tell me why that would be the case? Think of some ideas. Why do we lag the horizontal but we don't necessarily lag the vertical? Give you a hint, it's got to do with soil movement. So what that lagging provides is that's a compressible foam. So it's 10 millimetres of compressible foam. You do 2 layers of that, well, 2 layers for your low reactivity and your medium reactivity. For your high and extreme and P-class soils, you do 4 layers. It's this spongy sort of foam, which is strong enough that if you were to pour concrete on that, it doesn't collapse. So your dish sponge sort of foam, that would be too soft. That squashes up. This is much more rigid than that, but still it's compressible. So when we get concrete poured around that, and we've got some soil movement lifting up our slab, moving our slab around, and our pipe that goes through there, which is obviously going through the soil. That pipe, back here might want to stay put, whereas our slab is moving. We're going to want just that little bit of free space for that pipe to be doing its thing. The way that we can guarantee free space around that pipe is to have wrapped it in a spongy sort of rubber, so it can move like that within the pipe. Well, the pipe can stay in the same place while our footings move, for example. Because what you really do not want to happen is, if this is the outside of the building, if we get a crack there, it's bad, it's not game over. If we get a crack there, that's really bad. Because that sort of thing is very hard to rectify. It can be rectified by sleeving inside our pipe, and it's not a very easy process, or we can decommission that pipe, cut a trench through the slab in another area that's not going to affect it structurally, and send the pipe out. But whatever the scenario, it's not cheap. And so we want to ensure that pipe can move a little bit independently of the slab. So lag the pipes, and you're going to want to, if you're going to be inspecting a site, you're going to want to see that sort of thing is done. Exposed pipes are capped or taped. Any idea why you'd cap all your pipes?
Get concrete in.
Exactly. Yeah. Once again, you get concrete in your pipes, that's game over as well. That's especially if the concrete goes off and sets inside your pipes. What are you going to do? Then termite treatment. You might want to spray the soil at this point. Depends what your termite treatment's going to be. That depends on what your client wants or what you specify. So one thing you can do is spray the soil down. I don't think that's the best. You can put in a vaporproof membrane that has termiticide inside the vaporproof membrane. That'll stop. So when the termites go to eat through there, they'll get poisoned. They'll go, be put off or die. You can use Termi-Mesh. Is there anybody familiar with Termi-Mesh? Yeah, got one.
Is it strips or sheets in a roll? Or?
You can get it in strips. So the area that you use it in strips is around the perimeter of the building, underneath your brickwork. So that makes sure that termites have to go around your bricks. But essentially, a concrete slab does that same job anyhow. So typically, it's not used on the perimeter. They just supply it for that. But where it is used, and you still get it in strips, but then you bend those strips around your pipes in a fashion makes it look like it's wearing a little tutu, like a little skirt on your pipe. So you've got your pipe doing this, and then you've got your mesh wound around your pipe doing that sort of thing. And then you put a hose clamp on here like that, binds it all really close to the pipe, and that mesh flares out around that pipe. And then when we pour our concrete slab, that gets embedded, so our pipe is going through, that mesh gets embedded in the concrete. The reason we do that is because while our concrete is going off and curing, it shrinks slightly. So it loses some moisture, and the whole thing shrinks just that little bit. And we'll get, a 1.5, 2 millimetre gap at times between our pipe and the concrete there. So that tiny little gap, that's enough of a gap for termites to go through and work their way into the building. But if you use that mesh around your pipes, that mesh gets embedded in the concrete and the termites can't get up through that little gap that happens around your pipes. So those pipes don't have any Termi-Mesh on them. I wonder if we've got a slide that shows it. No, we don't. So underneath our slab, we have to put in a moisture barrier. So for any, occupiable residential building, you have to have a moisture barrier underneath. It's called a vaporproof membrane. It's stop water vapor, getting to the underside of the slab and working its way through. But basically, it's a moisture barrier. So 0.2 millimetre thick barrier of plastic polyethylene film placed over the surface and in trenches to prevent moisture penetration, lapped and taped at 200 millimetre laps, and it's taped to provide a waterproof seal. So once the concrete goes on top of it, that packs it fairly well together. But until then, you lap those joints 200 mil and you tape them. It's done with this grey tape, which is fairly stretchy, sort of sticky stuff. And then also and you can imagine it. So you got your vaporproof membrane set down there, and it's in the trenches and things like that. And then you get people walking across it with steel rods and carrying mesh and putting all the steel in there. You get holes poked in it all over the place. It's pretty strong, stretchy stuff, but still, end of a reinforcing bar with a guillotined edge, they go straight through. So you take up any of those penetrations as well. So that all happens. and then you also tape it around your pipes as well. So then we set all of our steel work in there. And you see on this is maybe it's a bit hard for you guys to see back there. Yeah, no, you can't really see it. What's going on here is we've got a whole heap of bars set along the top of our beams, and then somebody's placed some bars that go across the beam like that all these bars sit on. You do that until you get your ligatures in place. So these are your bars, and this wire cage around there are your ligatures. I didn't draw it on this one here, but typically when you're doing drawings of a cross section of a slab and you're drawing your ligatures, it's a good idea to. This one's a bad one, is it? It's a good idea to draw your ligatures so they go around past that rod and they bend back, and then this one coming up here bends back like that as well. Drawing your ligatures like that, that's really the correct way of installing them. So they bend, so where they finish they bend around. So that's one continuous piece of wire that they bend over that like that to help lock that bar in and help retain their structure. So yeah, there we've got a bit more of a clear example. So fixed into trenches, tied into a cage and lowered into trenches. Spacers are used to provide the correct separation and cover to concrete. So these are our spacers here, and they're called bar chairs. So we have standard, edge distances for our reinforcing. We don't want to have our steel reinforcing like only 10 millimeters away from the edge of our concrete beam, because moisture still makes its way into concrete a little bit. And when steel is in the presence of moisture and oxygen, it rusts. And that rust on the outside of that steel it expands and it pushes the concrete out and pushes the concrete off. So I'll draw close. So this is our footing. Dodgy one as well. And if our reinforcing is right there near the edge of that, it rusts and it pops the concrete out. And has anybody seen that before in places? You see it particularly by the seaside, places built in the 60s or so where they weren't really thinking about that. Put steel in the concrete, that presence of salt and whatever makes those rust and pops concrete out. So we've got what's called concrete cover or edge distance. So these bar chairs, they set it up 40 millimeters or 50 millimeters away from the bottom. So you have to have 40 millimeters cover for internal spaces, 50 millimeters cover for any external. So specifically height chairs use plastic or concrete blocks. Minimum cover 25 top of slab, 40 millimeters to sides of beams. I might be wrong about that. I thought it was 50 millimeters for external, but maybe it's only 40. So fabric is lap and join 2 panels of fabric in width. So when you're estimating how much of that, so we use the term fabric. Other terms for that is slab mesh. That's this stuff on top here. So and I can't think of it off the top of my head. Typically you use SL72 mesh for your residential slabs. I think SL72 or SL82. I can't think of what. Does anybody know what SL72 means or what SL82 means? What the? I think 82 might be 8 bars per mesh square. 72 is 7 bars. It's something like that. I can't remember. But the SL72 comes to mind with residential slabs. Anyhow, that's how your mesh is defined. And your mesh, you have that to lap it over 2 squares, and then you tile those bits together. Has anybody seen people fixing steel with their little wire ties. The old way of doing it is you get these wire ties and this little tool that you can whiz it down. Now they've now got a battery operated tool that you just walk up and go bzzz, bzzz, and it just wraps all these joins in a bit of wire, ties them all together. So that's how that happens. You have to lap them too because it makes a nice solid workspace to be working around. Oh, there we go. That's our termi mesh there. So termite protection stainless steel mesh can be used in lieu of chemical spray. Termite mesh used at the perimeter of the slab and at penetrations. Chemical spray to slab area and to sides of trenches. And that's and that's the taping of any of those gaps and so on. I've talked about as well. Some more examples. So looking at that, we're dealing with a fairly reactive site. There, it's a very deep trench, and what appears to be 16mm bars, and 3 of them for an internal beam. So don't know what we've got on the bottom of that edge beam there, but we've probably got some fairly large reinforcing happening there as well. And pretty close beam spacing as well. So I see that and go, oh, that's been designed for a fairly reactive site. So these are our ligatures that hold all of our bars in place, provide that cage. And actually, probably, I don't know if you guys have been coming to the TAFE much through the semester, but you've seen a lot of the works happening out on the road here, and the really big mesh or the reinforcing cages lowered into holes. That's been some pretty impressive reinforcing going in there, but it's the same scenario. You've got these bars, and they've got the ligatures to hold them into a cage, and then they're lowered into holes to produce piers. So here's another picture. Any ideas of what's going to go there in that corner? Bathroom. Yeah. How do you know that? A lot of plumbing. Yeah, a lot of plumbing. You've got a 100mm pipe there. What's that for? Toilet. Yeah. 100mm pipe, toilet. 40mm pipe for floor trap. 65mm pipe. That's external inspection for our toilet actually. Is that a 65? I don't know. Yeah. Bit off. Anyhow, so 40mm for your floor trap. Sometimes 65 for your hand basin. And it looks like we've got another toilet happening over here as well. Or maybe the yeah, that one definitely looks large, doesn't it? Probably 100mm or so. I don't know if the perspective is throwing it out. Because you're not normally going to have 2 toilets that close to each other in a house. It's weird. So formwork, timber or steel forms are used to form slab edge and used to form set downs and rebates. So oiled to allow separation and staked in place sufficiently to resist concrete pressure from the pour. That bit has to be done really well. If it's not done really well, you get bits of formwork which collapse, and that's bad case scenario on a site when you've got a concrete pour. Because you order enough concrete to do your slab, if you get a blowout in a section, well then that really throws things out and may mean you don't have enough concrete. And also, a concrete pour is frantic enough as it is. That has to be set out really well because you can't have any problems during the concrete pour. Constructed with form ply. Has everybody seen form ply before? It's nice stuff, black surface to it, really strong plywood. A bit more expensive than your standard ply, so about around $50 a sheet. Also, forming of set downs and whatnot, that's actually fairly similar. It's done during the pour, or typically it's done during the pour. Sometimes you set your formwork out for your set downs beforehand, but it's just in this one they haven't. So they'll be doing their set downs as they pour the concrete. And the way they do that is they'll have a location marked on here for where they're wanting to do their set down. they'll pour a little bit less concrete in that bit there, and then they'll make it to till it's 100 millimetres deep or so to whatever depth it needs to be. And they'll put a piece of timber across that, so they'll get that nice and level. Get their piece of timber there, and that timber has to be in just the right position and held in place, and then they pour the rest. So you end up with I don't have a pen to draw it now. A bit of concrete, and then your piece of timber, and then a lower section of concrete on the other side. Does that make sense? So quite often it's done actually as they're pouring. With old formwork as well, you couldn't really do this sort of thing. Have your bars going up higher than your forms, because typically you used a screed across the top of your formwork to move that concrete around. Now people have motorised screeds, so it's a big aluminium bar with a motor on the top. You pour the concrete in there and like this, and it moves the concrete around without having to screed off the top of your formwork too much. Much easier. Oh, we've got there. Placing the concrete. So you have to give a day's notice to council and engineers for inspection. Concrete placement is a continuous process. So with your residential slabs, it happens really quickly. They pour the whole slab really quickly. With your really big sheds and warehouses and things like that, it can happen over a day. They start pouring that bit and they move along. You can't really do that with a residential slab. You don't have that distance, and for concrete to be going off and solidifying over there while you're still working on other bits. So for residential, typically it happens really quickly. Placed, it's vibrated and screeded. Concrete needs to be vibrated into place to make sure it gets around all of the bits of reinforcing, etc. So the way it's vibrated is there's a little two-stroke motor and a flexible, this flexible tube on the end of that, and it's got this metal bit on the end which vibrates really quickly, and you plunge that into the concrete. It makes all the concrete settle down, so it vibrates it all, settles it all down around the reinforcing and brings all the air bubbles up. So it's vibrated and then screeded. So screeded is the working of the timber across the top. Now if you've got really good people who are placing the concrete, you don't have to do much screeding. They'll place it really well, so you're not having to move a lot of concrete from one position to another. If you've got somebody who's not placing the concrete well, then it's a lot of work. Screeding. It says timber or metal boards in a chopping motion to assist compaction. Now you've also got the option of motorised screeds as well, which really helps out. Isolated pads can be used to achieve correct level using a laser level. So that's another way of working out to what level you're doing that concrete throughout that slab. Is you do some little bits about the place and trail them down till they're just at the right height. So you set that with the laser level. You go, okay, all those are just at the right height, and then we fill in between all those. So we use those as a guide for placing the concrete. Concrete is then compacted using vibrator at 500mm intervals until water and bubbles stop rising to the surface. You also have to avoid hitting the reinforcing with the vibrator, because if you hit the reinforcing moves around inside that concrete and it pushes all the aggregate away from the reinforcing. So you get weaker concrete around your reinforcing. So that has to be avoided as well. What we can see in the pictures here, it's our concrete truck driver. You've got a chute which comes out the back of the concrete truck. So those, you'll see here, he's got his bit of chute just folded up there, and he's got another bit of chute here. Typically on the back of your concrete truck, you just hold this whole series of these bits of chute that you can just clip onto the end of others. So you can have a really long chute coming out of the truck, and you just move it around like this, and the amount of concrete that's coming out of that is dictated by this guy who's normally sitting in the cab. You will tilt the thing a bit more and send a bit more out or not. So you're going to be in contact. You've got to be able to see him in the mirror all the time, and you're telling him whether you want more or less, or to stop or whatnot. In this scenario, he's going straight into a concrete pump. So that's a truck with a big hydraulic pump and a hopper on the back. That all the concrete goes into that hopper, and then it gets forced through this. Do we have a boom? No, I don't see a boom. So it gets forced through this tube, and then that tube. So these guys are the unlucky ones. They've got the tube that sits on the ground, and they move that around. It's got this metal bar that comes off of it like that. It weighs a ton. And you move that around. The lucky concrete workers have a concrete pump with a boom on the back of that. So the pipe goes on this boom and it comes down and just hangs there. And that can be driven around electronically, or it can be moved around a little bit manually as well. Has anybody seen one of those booms operating? There's probably been quite a few operating on South Road here. So that, concrete pump makes things much easier. The old way was to, for less accessible sites, you had to get concrete in the wheelbarrow, you barrow it all in. That's a crazy amount of work. This way, it's all pumped through that pipe and placed. But by far the easiest way is where you've got a boom and you just place it all around in that fashion. So, finishing the slab, determined by its use. So, screeded for tiles. So for tiles, you want a bit of a rough surface there for the tile adhesive to adhere to. You don't want a really smooth steel troweled finish on your floor if you're going to tile it, because the tiles won't bond as well. But you trowel for vinyl and carpet. Or if you want to do, has anybody looked at a new Bunnings warehouse and looked at how nice the floors are? Seen that before? You got some, they get some amazing finishes in their warehouses, and the way they do that is they've got their, we've got one of those, these dudes here. So it's a steel trowel, well, a motorised steel trowel that you can actually sit on and zoom around in, but they will spread little bits of cement with that as well. So you get this cement-rich slurry on the top, and then this machine, which is just like a big version of that, and that one's called a helicopter, it trowels the surface to get just a really glassy, smooth finish. And the more you work that surface and you keep working it, the smoother you'll get it. And then you keep adding little bits of cement to make that top section really hard. So the majority of your slab might be 20 MPa concrete. What you get up the top, it might be 50, 60 MPa concrete, really hard concrete on the top, but a glassy finish from lots of steel troweling. And you can use that as a finish for the floors in your house as well. So there's the option of polished concrete in a house. If you want to do polished concrete, you have to have minimum of 32 MPa concrete. Several ways to achieve that. One is to do the whole slab in 32 MPa concrete, a little bit more expensive, but it's easy. Another way to do that is to do a cement-rich slurry on the top, cheaper but more technical. So it relies upon the skill of your concrete layers. But you've got to get that 32 MPa at minimum for the top section of your concrete, and then you've got these diamond blades and you cut that concrete back. Some people like to cut it back to the aggregate, to have exposed aggregate. I guess everybody would have seen that at some point, polished concrete with exposed aggregate, cut right back. Or you can just cut that first little section off the top. You might expose some aggregate, you might not. But then, or the other way, the cheats way of doing it is with a steel trowel to get that non-cut back concrete look. Right, but I'll better move back. So, allow bleed water to rise to the surface. Do not use dryers as they cause deterioration of the surface. Finishing should be done when a suitable hardness is reached. So you go checking, and typically when you're doing a slab, the concreters will work at 7 o'clock in the morning. That's their first chance to make noise. If the neighbourhood, if the council allowed you to make noise at 6 o'clock in the morning, they would be there at 6 o'clock in the morning. They want to get there as early on site as they can. The reason for that is because they might have to sit around for 5 or 6 hours before they can do that. And so you get your concrete, and it's a mad dash to get all your concrete in, but then after that, it's a lot of sitting around and waiting, till your concrete is hard enough. And this, looking at this still looks too soft to my eye. Like, he's got concrete coming off under his boots, but it's got to be hard enough to lift that helicopter on, and you'll soon see that it's not hard enough, because you get bits of concrete flicking off all over the place from your helicopter. So it has to get to this sort of hard consistency where a steel trowel can do a nice finish on it. So you wait for all the bleed water to rise to the surface and then disappear, and then the floating of the slab can proceed to produce a surface texture ready for finishing. The surface finishing pushes aggregate beneath the slab surface and closes any cracks. So troweling provides a smooth, durable surface. Process is either by hand, wood or steel, float trowel, or machine, helicopter. And I can't really see. Yeah, not sure. Oh, I reckon that might be the concrete vibrator. That's a really big one. It's a very cumbersome one. So there's a 2-stroke motor and a flexible bar that comes off of that. They use that for vibrating the concrete into place. So that's obviously that's a really big commercial project where they're trailing off this section here when that section's still yet to be poured. So they'll probably be working out the lights later on in the night to finish the rest of that. So there's a good example of getting your bathroom set down happening. So you pour that section first, and then put your timbers in place, and then you can pour your concrete higher on the outside of that timber formwork, and you end up having something like this. Everybody know why we do a set down for a bathroom? Explain that.
So you can screed the floor before the tiles.
Yeah. You don't. If we did do a set, so you always want your whole floor sloping toward that floor trap, or you want to, how do I say, you shower, and that's why we've got a separate set down here for showers. We want all of our shower floor to slope toward that floor trap for shower, but for our main floor trap here, we want the rest of the floor to slope towards that. The way we achieve that is we do a concrete slab floor, and then we do the screening for the tiles, which is thicker at this outside edge, thick like this, and it gets thinner and thinner and thinner and thinner, thinner till it gets to that there. So the whole floor slopes towards it. So that's all done afterwards. And then your tile adhesive goes on that, and then your tiles go on top of that. So to achieve that, we need a set down. If we didn't have a set down, then we'd get to our bathroom, we'd have a step up about this much at the door, and then it slopes down. It's not a good look. I think that's about all, which is fairly notable in those. Oh, can anybody tell me what type of slab that might be? Just looking at it. A waffle? Yeah. 10 points. Yeah. So it's sitting up above the ground, that sort of 400 millimetres or so.
Oh, so there's no trenching in it?
No trenching, yeah.
Put the boxes on top.
Yeah. And also I didn't mention before, you put your vaporproof membrane just flat on the ground before you put your boxes on that as well. So it's super simple. You get just a really flat site, well, obviously with all your pipe work poking up through where you want the pipe work coming, so that's all set in place, but then it's really flat. Then you put your vaporproof membrane down, and these waffle pods come in these big, they're all bundled together in these really big bundles that looks impressive because they're massive, but they're super lightweight. You can carry them like this, you break them up, and then you just set them out like that with the pod lock spaces in between them and run the bars between that. Happens really quickly. So curing is a process to control the loss of moisture from concrete after placement. If not cured properly, concrete will dry out too fast and produce a loss of compressive strength and poor durability. Has anybody ever put stuff in the freezer or you get buy a fish or something, that fish has been blast frozen, or you get a fresh fish and you put your fresh fish in the freezer. The blast frozen fish ends up being a much nicer. Actually, it's not a very good analogy. I might use something else. But when you freeze something really rapidly, you get these tiny little ice crystals, and when you freeze something really slowly, you get big ice crystals. You ever seen that before? And that's because when stuff freezes really slowly, those water molecules, because you've got your H hydrogen with two oxygens, it's got negative poles on the oxygens, positive pole on your hydrogen. It wants to form into a lattice, and that's why you get crystals. So you get all your molecules forming into this lattice, and if it's given time, it forms into a nice lattice forming large crystals. If you make it freeze like that really quickly, you don't get that lattice happening. And that's the same thing with concrete as well, and that's where you get your strength. So if your concrete dries out and goes off really quickly, you don't get as good a lattice happening in your concrete. But if you retain that moisture, you slow it down, you keep it cool, stop that moisture loss, you get much better lattice in your concrete, and that's the curing. So how do we make that happen? One way of making it happen is we cover it with sheets of plastic. Another way is we spray periodically with water. Sounds a bit too involved for my liking. Or use a curing compound. So a curing compound is something you spray on top of the concrete slab once it's been put down, and that forms a barrier to stop all that moisture coming out of the slab. So it slows it right down. Here's a detail, external beam detail and internal beam detail. We won't go through that, I guess, too extensively. It's something for you to check out at home. You'll become very familiar with this detail. Some of the obvious, bars and ligatures got a set down brickwork. So your timber frame that happens up at floor level, but your brickwork happens a little bit down a little bit lower. You want that to happen because you get moisture in here. You always do. And that will at least go to here. It won't go into your timber. Yeah. Slab mesh at the top. For the rest, I'll let you pour over when you have to draw a section through a concrete slab. So some other cross sections through a slab, various other things. So that's pretty normal sort of thing. And then we have a slab thickening for a load bearing wall. It's more than 1 metre away from internal beams, so we don't have to produce an extra internal beam for that. We just do a slab thickening for it. It's an interesting scenario. I haven't seen that scenario with a residential building before, where we've got basically a concrete strip footing with a slab located on that strip footing. We see a lot of that sort of stuff happening with civil works, with drainage and whatnot, but not. I don't know where Jason sourced that image. It's an interesting one. The other one is fairly standard. This detail is a common one for when you're using concrete blocks. Everybody knows what a Besser block is. Besser is a brand name, but in South Australia we just call them Besser blocks. So there's a bit of construction out there happening with Besser blocks. So concrete blocks, fairly rapid to go up because they're 390 millimetres long by 190 millimetres tall. 10 millimetre mortar gap. That's 400 millimetres of wall with every block. It goes together very quickly. The great thing about Besser blocks is they can also be core filled as well. So if you look at the top of a Besser block, I'll get another pen. one will hopefully work. So, top of a Besser block, I'll just draw it over this one here. So, looking down on a Besser block, looks like that. Is that familiar? Thank you, everybody. And so, we put one Besser block down, and then we go to do the next course. Our next course, we stagger the Besser blocks. So that one goes there like that, and we've got. So these squares, they all line up all the way down. That's what this is about. So when we're doing a Besser block wall, typically if that's a retaining wall, we want to do a core field block wall, we'll put a bar in there, and this little bit here, that's called a cog. So if you're working in an office or something, and then someone writes 10 mil bar with 50 mil cog, you know how to draw that. That little foot's called a cog. So it means you bend it back at 90 degrees. So that's set into concrete. I don't know. Let's say 100 millimeters embedment. So that's referred to as embedment. So cog and embedment. Got your rod set in there. Now, quite often you'll just set in what are called starter bars. They'll be, let's say 600 millimeters tall. So you do a starter bar, and then you put a rod in later on. But let's say, that sort of example is not very buildable. You don't get builders working with massive big rods sticking up in the air because they're doing this all the time. But let's say they did that, right? They get a bar, goes right up like that. That bar, it's got to sit right there in plan view. So our bar's coming right through, and then we fill this whole space with concrete. Sets that reinforcing inside that concrete block wall, makes a very strong structure, like that. So that's with your Besser blocks. You can also do something fairly similar with bricks as well, but with bricks it gets a little bit more complex. So we set down one leaf of brickwork, here. We set down another leaf of brickwork like that. Well, let's say I did a better job and I staggered my joints between the two leaves. But we got 100 millimeters between the two. You can also do a core filled brick wall as well. The reason that they're tricky is because you're limited to the amount of concrete that you can pour into that wall at any one point in time. And it happened to a wall that we specified. It might have even been me that made a mistake. I don't know. But we specified a section of brick masonry wall to be core filled, and then you specify in 1 metre lifts or 1200 millimetre lifts. That relates to how deep that let's say this is elevation view of our brick wall. The bricks here like this. We pour concrete in there to only 1 metre depth, and then let that consolidate. Then we do another 1 metre lift, let that consolidate, and then you do the final bit. I don't know. I never got reprimanded for anything, so maybe they specified it. I don't know. Anyhow, so what happened was the builder just filled the whole thing up with concrete straight away, and it popped out, and made a big mess. I guess not a really expensive thing, but horrid mess to clean up. So with brickwork it gets that a little bit tricky. You have to specify the lifts. You have to say in X amount of lifts, because if you just fill the whole thing up, they go all over the place. Besser blocks far more forgiving in that fashion. You fill the whole thing up, that's fine. They're relatively wide. They're not going to go anywhere, and they're all tied together. But that's what, at the end of the day, that's what that detail there is. And also that detail, 10 mil rod going all the way through top to bottom, that provides you a tie down. So you tie this one, you've got your top plate there. The way that one is tied down, it's got, so the 10 mil rod goes through the top plate, and it's got a washer on there, and I assume that's a threaded rod, or for a threaded rod for a section. Bolt or nut on the top, so our top plate is tied down to our wall. We can put our rafters on top of that, and that's going to tie the whole roof down in the event of a cyclone or whatever, that rod going all the way through. So it provides a very strong tie down. Let's see. Yeah, I better press on. There's some other things I could say about that, but should move. So alternative footing systems. Waffle pod, know all about that. Pier and beam, pier and slab, and grillage raft. So I'll try to move through pier and beam and pier and slab relatively quickly because there's a lot of commonality happening there. Grillage raft, we'll spend a little bit more time on. So waffle pods, we know those fairly well, so we'll move fairly quickly through these as well. So developed by Cooper engineers, constructed on a level site, no excavation, etc. Yeah, now we know all of that. We know all of that as well. Here's some pictures to see it all going into place. Yeah. So as you can see, it happens. You know, it can be set out really quickly. It's very, very quick and easy. So here's a drawn detail showing what's happening. Pier and slab. So did I move? I've given enough time to waffle pods, haven't I? You guys cool with that? Pier and slab, suitable for reactive soils, and as I mentioned previously, so not all reactive soils, so it does depend. So depth of piers depends on the depth of suitable founding material. Also another situation where you use pier and slab, so we've got reactive soil, but a far more common scenario is where, I'll just draw straight over these ones, got a hillside like that. So we're looking at our hill, we want to build a house on the hill. The way we go about building that house, now Adelaide or so within your hill space zone, they don't like this very much, but let's say we're building it out at Macclesfield or something out there where the people on the plains aren't going to be looking at it. We'll dig this bit out and we'll put all the soil there. Has anybody seen that before? I dare say people have seen that scenario before. You dig a bit out, dump it all here, although it ends up being that sort of shape, like that. We've got a bit here. We would use, if that bit's, you know, really quite deep, much deeper than, so if our footing beams are deep enough to hit the natural ground, it's not really an issue. If, you know, if our beams are going to be that sort of depth or whatever, we do piers down into natural ground, because this soil, all this here, gets dug out, and yes, you've got your excavator driving over it, whatever, compacts it to a certain extent, but doesn't compact it to the extent that an engineer likes. So the engineer says, right, well, what we're going to have to do with that scenario is do some piers there to lock into that natural ground to hold that slab up. So that's your really common application of this. And also that, you know, and sometimes you buy a site or work with a site where that sort of thing has happened. You know, they've done that sort of levelling 20 years ago. You've got, you know, you can take some soil samples, but really you've got no idea of what's going on in there as well. You don't know whether they, you know, dumped a whole heap of timber or something and then did stuff over the top, you know. So once again, piers help you with that sort of scenario. Depth of piers depend on the depth of suitable founding material, fairly straightforward. Piers may be under-reamed to increase the bearing area of the pier. So it takes a special auger to do that. So an auger is one of those spiral type thing. In fact, do you guys see the massive augers out there on South Road doing those? Yeah, amazing. So, you know, you're not going to have that for a residential situation. But that's what an auger is. You can also get an auger that has these bits that, so your centre tube is hollow and you've got these bits that once you've dug down into the ground, you activates those bits to pop out and they cut out this section underneath, pull them back in and you pull your auger out. So you end up with a hole that's shaped like that. That's a fairly poor example, but like a bell pile scenario. So your auger cuts a hole down and then the things flick out cut that section out in there. Great thing for both, providing additional bearing for your pier, because a pier, it can be massive, great big pier, but you end up not having a great deal of surface area at the base. So a lot of concrete, not much bearing with a pier. If you ream out the base of that pier, you can get a much larger bearing onto that soil underneath there. So, if the soil is slightly compressive or something, that's a real bonus. So it does that, but also what it does is it locks the pier into the soil as well. You try to pull that up, it's locked in there as well, and that can have its benefits in some situations as well. Something that's not covered in the lecture notes, but it's getting used a bit more, are screw piles. Has anybody ever seen a screw pile? If you're doing structural engineering, you'll probably come across them. So they're pretty groovy things. There are various different manufacturers of screw piles for various different quality. The best quality ones are made with a stainless steel tube, 50mm tube, and then they've got what looks like a piece of an auger on the end of them. So this little spiral type thing on the end of them, like a corkscrew, really, like a really simple corkscrew that screws down into the ground, and then this 50mm stainless steel pipe, that's your pier for building on top of. So fantastic for like temporary structures and things like that. I saw one application, they built this thing on some dunes in Kangaroo Island, screw these things down, do a building on that, there's almost no disruption to the dunes whatsoever. So you've got this thing, do a thing on top of it, and then later on you can take it all away, unscrew the piles and take them away. There's very little disturbance. Fantastic for that, but also fantastic for a scenario whereby we've got this bit of soil here, it's really reactive, it's doing all sorts of things. This bit down here is not. Send a screw pile down there, locks into that soil very nicely, because as it screws down it doesn't do a whole lot of disruption. Just locks into that. Then we build our elevated timber, suspended timber floor or whatever on top of that. This bit of soil here, that can be doing whatever it wants, because our screw pile is locked into the nice stable soil underneath. It's another advantage. But screw piles can also be used in conjunction with a concrete slab as well. It's not super common, but in some scenarios engineers will specify that as well. Cool. So I'll just move through this pretty quickly because it's very similar to our integrated raft slab. So mark out positions, holes, blah blah, reinforce the cages. Underslab build its place at the slab area. Now I'll let you go through that at your leisure if you wish. The stages are not all too different. And then cardboard formers then installed over the slab area to form a platform. This forms a bench level for the slab. So in this scenario, they're casting beams and they're elevating the floor slab off the ground with, in this area, like cardboard formers, but that can also be styrofoam formers like waffle pods, for example. Separate that slab from the ground so that when that ground moves, those formers can be all crushed. It doesn't matter. But that's, beyond that, it's very similar. So pier and beam. So as I said before, you don't get many examples of a concrete pier and beam. Typically, it's all happening with timber, and that's what we've got, in our examples here as well. So timber posts on top of concrete pad footings, so piers and timber beam. We've got some pretty groovy bracing happening there. Sometimes you get this scenario. So your masonry piers and then a universal beam on top of that. So that's an I-beam on top of that for larger spans. But in some scenarios, and you'll see it in commercial construction a bit about the place, you have piers and then you have concrete beams cast on there. Of course, it's a little bit tricky. You've got to make formwork for this beam and then put reinforcing in there and fill it up. It's a decent amount of work, and you've got to make, I'll say, bespoke formwork for that beam. It's formwork you're probably not going to be using anywhere else. Whereas if we flick our mind back to our slab on ground, what do you call it? The formwork for our concrete slab on the ground, just straight lengths. You're just going to use that for slab after slab after slab after slab. Much cheaper because formwork is quite expensive. So, a bit about pier and beam, or some cross sections of pier and beam. So, yeah, once again, with suspended timber floors. Pier and beam sequence, I guess we don't really need to go into that too much. So it's pier holes, board and foundation, piers maybe underream, but put some reinforcing into those piers. We can use some void forms to hold beams up off the ground. It allows for any soil movement. Grillage raft, that's what I wanted to say about the last 12 minutes for. So grillage raft, it's much like your standard raft slab, except, what's your difference here between grillage raft and your standard raft slab? Noticeable difference. Well, standard raft slab and then grillage raft. Your edge beams, down 1200 mil or so in the soil. It's a really deep beam. So you see those around Newton-Ross-Trevor area. Remember where I said, okay, we've got this brown patch up there, really reactive soil. That's what you do in those areas. So you excavate your trenches really deep. Have I explained this much before about, you increase the depth of a member, you significantly increase its strength and flex? Do you guys understand that at all? So, like trusses, floor trusses. Has anybody seen timber floor trusses before? Maybe it's something I need to go into a little bit, but with your timber or your composite timber steel floor trusses, you've got a piece, let's say, a piece of 90 by 45 timber along the top here like that, another 90 by 45 down there like that, and then you've got these steel webs that go like that through there. Has anybody seen anything like that before? Now, if I took away those steel webs and I just used two 90 by 45 bits of timber, and I stand on those two 90 by 45 bits of timber, it's going to go like this. I'll be able to bounce quite well on that. If I separate those 90 by 45s with a bit of steel webbing like this, so I increase their distance apart, I stand on the top of that, there'll be no flex happening. That's really quite a strong section. The way that works is that, to put simply, when we put those two members further apart, but hold them still stable so they react together, they're operating as one unit, the further we put them apart, the greater the strength they're going to have to resist that bending moment. We put them close together, they get far weaker and we can start to bend it. The reason, so that's all about, it's about what we call a moment. So it's about the leverage. So you'll notice you get a really long bar and you can bend something quite easily. Use a really short bar, like say you've got wheel nuts on a truck or something. Try to do it with a short bar like this, it's not going to happen. You need a really long bar to crack those wheel nuts on a truck. That moment, that leverage you get from a long bar, same deal, same sort of scenario is happening here. You separate these further apart, leverage in this way, makes that stronger. And that's what's going on with our grilly draft as well. So instead of going out really wide, like making our footings 900mm wide footings, because that's used a lot of concrete, but it doesn't give us as much strength as putting all the concrete further down. And yeah, does that make sense? So that's why we would do something like a grilly draft. Now, to do that, typically you don't do that in one pour. In fact, I'm not really sure why. And that's an interesting, I'd never asked a question why of that, but typically it's not done in one pour. You pour deep, you pour your concrete down deep, but you continue your ligatures up through, and then you pour your slab on the top. It's done in several different lifts. Possibly it's got to do with compaction of concrete, so you can only vibrate concrete to a certain depth, or so. But typically that happens in a two-stage process. Of course, has excellent strength for lateral movement like this. If you get landslide type scenario, well, it doesn't, it's not very strong in that way. But it's not what we have to deal with typically. So, grilly draft procedure. We'll go through this fairly quickly. So, compact the field, excavate the beams. Beams average 1200mm deep. Beams poured independent of slab, two-pour process. Moisture barrier is placed over fill and down in trenches. Reinforcement is placed in trenches. And earlier I was talking about 10mm bars, 12mm bars. So here in this situation, like 20mm bars and 28mm bars. So really big bits of steel. Hangers are supported by a top bar and combination bars being poured first. Construction joint is formed. Slurry is poured to the top beam before the slab is poured. And finally, strip footings. Earlier on, I mentioned Parkside Unley area about bluestone houses around there. Their soil is not nearly as reactive as some other areas that we're building on within Adelaide. The reason you get all this cracking happening in through that area is because the soil is reactive, but the combination of that, that moderately or moderate to highly reactive soil in that area with the traditional footing system, which was a strip footing system, is that strip footing system doesn't have the capacity to resist much movement at all. So the strip footing system is as it sounds. You have a strip of concrete, or in the case of our old stone buildings, close to the centre, big slabs of bluestone. So just big chunks of bluestone with a bit of mortar in between. Today we do a strip footing with concrete, much stronger. It's a continuous strip, and then, so in this case we've got a strip footing and we've got some masonry piers, or we can do strip footing and solid masonry, or we can do a strip footing and just timber framing on top. All sorts of options for structure going out of there. But our strip footing, as you can imagine, if you've got soil swelling under this bit here, cracks very easily through there. That's what's going to happen. If you've got that beam integrated with a raft slab, the whole thing just moves like this. Whereas with the strip footing, it just crack straight through much easier. Is that fairly sensible? Well, makes sense. Oh, once again, that's our core field concrete block construction there. We've got our start bars, etc. So, construction procedure. String lines are used, place formwork boards, and brace and peg in position. Any sleeves are placed in position for surfaces. Nails or steel pegs are placed to indicate the finished concrete level. Yes, no, not. Yes, maybe, not always. With laser levels these days, you can go and you just get all your formwork dead level. So your initial formwork set out, do that with a laser level, and so you get all your formwork dead level. Just screed to the top of that. It's another way of getting a dead level. Strip footing. Steel reinforcement cages are placed in position and concrete is poured and instead of compacted, I'd say vibrated down. And then the top of the beam, maybe float finished, depends what you're going to be putting on it. You're not going to want any more than about 4 millimeters variation with the top of your strip footing there. You've got to be doing masonry on top because you've got a 10 mil masonry mortar bed. You don't, anything that's over 4 millimeters gets pretty obvious in that 10 mil mortar bed. And that's all of our footing, all of our common footing systems covered, even with the inclusion of some screw piles and so on, and short mention of rammed piles that we may want to use in the levels. So that's it. That's it for for residential footings. We'll be revisiting concrete later on in commercial, and we'll be getting much more into concrete as a material and as a commercial application. There's some pretty groovy stuff that happens with it in those scenarios. Do I have any questions in regards to some of this stuff from tonight? Have I packed you full? Things to take away.
I'll be here all day.
Yeah. Yeah, I saw you much earlier. Yeah. All right. And any issues with assignments or so that need clarification beyond? Right. So thank you very much once again for your attendance. And best of luck with the assignment as we've got. Well, what have we got? Eight days left in which to complete a fairly weighty thing. So you're aware of that, John?
Yeah.
What's that? Yeah. What was that?
Yes,
Sorry.
yes, son.
What about it?
Serious.
Oh, okay. Yeah, that's fine. Yeah. Okay. So thanks for coming along tonight, and we'll.